the solution to this problem can be written in the form function of theta times function of phi. Okay, the way the math works out for this is it's very convenient to just write the solution in terms of function of theta times a function of phi. So that's your wave function. It depends on the two angles. The r dependence is gone because we're constraining our particle to be on a spherical surface, so r is constant there, right? So this function psi is, the function psi that we get here are known, it's famous in math, it's known as spherical harmonics, okay? And when you solve the differential equations, you come up with two quantum numbers. You can see here we have two variables here, you come up with two quantum numbers. Remember, particle in a box, one-dimensional problem, we come up with one quantum number. When we made it a square box or rectangular box, two quantum numbers came out. Okay. When we made it a three-dimensional box, we got three quantum numbers. Same idea here. With a particle on a ring, we had one quantum number m. And this time we have a particle on a sphere, you're going to have two quantum numbers, L and m. L, or you can use m sub L. Right? And it turns out that the restrictions, based on the boundary conditions, the restriction will be for L to be a non-negative integer. So L can only be 0, 1, 2, 3, 4, and so on. And that is known as the orbital angular momentum quantum number. And m, now you have additional restrictions for m. Whereas before we just say m must be 0, plus or minus 1, plus or minus 2, plus or minus 3. Well, this time, m cannot exceed plus or minus L. So it only goes from negative L all the way to positive L. Right? So, for example, what are the allowed values of m if L equals 3? M can be negative 3, negative 2, negative 1. Okay. Negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3. Or you can say it's 0, plus or minus 1, plus or minus 2, plus or minus 3. You'll notice you have three pairs, right, of pluses and minuses and a plus a 0. So you can say there's 2L plus 1 possible m values. 2 times 3 plus 1, 7. Okay, 1, 2, 3, 4, 5, 6, and 7. 7 possible m values for a given L value. Right? So how many allowed values for m are there if L equals 5? 11, right? 2 times 5 plus 1 is 11. So what are those m values? Negative 5, negative 4, negative 3, 0, 1, 2, all the way to 5. That's 11 possible values of m. Any of these sounding familiar? Remember quantum numbers for the electrons from freshman chemistry? You'll see later that the spherical harmonic will come up when we talk about the wave functions for a hydrogen atom. So these are the expressions for the spherical harmonics. This is what you get. Why can't I scroll this? So the way it's written, spherical harmonics are usually represented by the letter Y, and the number that you see down here is your L, and the number up here is M, sub L or M. Okay, so this thing right here is Y00. So what's Y00? It's independent of theta and phi. It's just, it's just 1 over 2 times 1 over square root of pi. Okay? Now, the dependence on phi, okay? Remember we said the spherical harmonic is a function of theta times a function of phi. The function of phi we already know. Those are the eigenfunctions of the LZ operator, which we looked at when we talked about the particle on a ring. So it's 1 over square root of 2 pi e to the im phi. So you've seen this function before. Right? So what's S of theta then here in this particular case? Well, this is going to be equal to, so this is a function of theta times a function of phi. What's the function of phi in this case? 1 over square root of 2 pi e to the 0, right? So this is s of theta times 1 over square root of 2 pi. So what's this one right here? That's what's that? Okay, so that's 1/2. I multiply this by 1 over square root of 2. Square root of 2 over square root of 2, right? So this will give me square root of 2 pi. So that's going to be square root of 2 over 2 square root of 2 pi. So I can factor that out. That's square root of 2 over 2 times 1 over square root of 2 pi, right? So what's square root of 2 over 2? That's just 1 over square root of 2. So that's your s of theta. And this is your t of phi. Okay? How about this one? What is s of theta for this thing? What is s of theta for L equals 1, M equals 0? Let's look at our function for L equals 1, M equals 0. Right there. So y1, 0 is a function of theta and phi is equal to 1/2 square root of 3 over pi cosine theta. So that's equal to s of theta, function of theta, times a function of phi. What's the function of phi equal to? 1 over square root of 2 pi e to the I times 0 times phi, right? And that's just 1. So what's s of theta? Oh, there's an easier way I could do this. I just multiply both sides by square root of 2 pi, right? S of theta would just be equal to square root of 2 pi over 2 times square root of 3 over pi cosine theta. Now, if we were to plot this function, you're going to find that theta equals pi over 2 is a node. Why do you think that is? What happens if I plug in pi over 2 here? What's cosine of pi over 2? 0. That's, if you go from 0 to pi over 2 to pi, cosine 0 would be 1. It's going to be dropping to 0 when you hit, until you hit pi over 2. And then it becomes negative past pi over 2 until you get to pi where it becomes negative 1, right? So cosine pi over 2 is 0. So you have a node at theta equals pi over 2. What is theta equals pi over 2? What kind of surface are we describing when we say theta equals pi over 2? Remember the definition of theta? If this is your xy plane, this is your z-axis, what did you say theta was? The angle that you have to sweep to get to a point from the z-axis, right? So if you have to sweep an angle of pi over 2 before you, in order to locate a point, which point are we referring to? A point on the xy plane, or in this particular case, more specifically, a point on the equator, because we're talking about a point on a sphere. Right? So we say that the midsection of your sphere is a node. The probability of finding the particle there is 0. Okay? So your wave function is positive above and negative this s of theta will be positive above and negative below the equator.